some additional documentation prepared. Just did a quick search around the internet. I found this is a Game Boy implemented in Go, so it might be interesting to look at as a reference. I've got this instruction reference. Always good to have one of those extra. And this is like a miscellaneous documentation for Game Boy coding. This is really aimed at people who want to build their own Game Boy games, and not really people that build emulators. But you know, might be useful. So this is, I think, a very well, let's say, famous piece of documentation, and this is the one I was using before, and it has really nice kind of you know, it's more concise information, so it might be useful. So one thing that we need to do is we need to have a look at the CPU code, because I changed this a little bit. Need to update. So I've added, I've changed the way the registers work. These are all 8-bit registers now. That's the way I implemented it. Except for the stack pointer and the program counter, these are still 16-bit. So 2 registers together. And the reason for that is you can actually address all these registers by themselves and by their 16-bit version. So I figured it is the easiest to implement it in the most smallest form, and just use special get and set functions to address the 16-bit portions. What you see under here is something I've been setting up. It's just a large collection of all the a part of the load instructions that we'll need to implement. And these are like all the different addressing modes. So I've used these numbers I can use to reference them to the documentation, but basically each of these loads are a different way of loading information from and to the memory, or switch them between registers. So for instance, this one will load the contents of register 2 to register 1, and most of the registers can be used in this instruction. But then there are a lot of different options, so you can use just a value, or you can put a register into another register, or the accumulator into the register. They have all different kind of specs. So one instruction might take only 4 cycles, some instructions take 8 cycles, some instructions take 12 cycles. These one are interesting because you can use these load instructions to get a value that is in the HL register, but not the value itself. In the HL register you have an address, and then this instruction will dereference that address, and that will get the value, and that will be put into A. So there are a lot of load instructions, and I haven't even built them all. That they're not built and just do nothing right now, but these will be implemented at some point. Then I have here a couple of setters and getters under this, and these will be used for our own code to, you know, set registers a certain value. So when we implement those load instructions, when we implement you know, add, multiply, I don't think there's a multiply instruction, add, divide, also I don't think there's a divide instruction, add, subtract, all that stuff, then actually we'll be using these functions. So these are the 8-bit values, and these are the 16-bit ones. And you can see that I'll quickly explain this code. This is a binary, binary AND operation. So we have some kind of 16-bit value, and then I need to extract the lower part of it to put it in A. Or actually, I think I've done this wrong. I think I need to switch them around. Well, we'll come to that. So I'll mask one part, all zeros. So if you end this with all zeros, it will become all zeros, and these are all ones. So whatever is in the lower part of val will be put into A, and the same goes for F. But I think I've done it the wrong way around. Same goes for F, but then we need to shift it over. And these ones are just simple because you cannot use them in their 8-bit singular form. And then the same thing for getters, but they're really simple, of course. So then have built some like generic register functions, and I think that my idea will be to use these as much as possible, because it's more well, it's more Pythonic to do it in this way, not use all the individual instructions. So what I've built of this, I actually got this idea from the Python documentation, because I was looking for a case switch. Most programming languages have a case switch in which you can specify, a large number of cases. So for instance, you have a value that's an integer and it can hold any integer, and for a number of integers you can then specify a bit of code that needs to be executed in that case. But Python doesn't have a case switch, and but I still want it to be as fast as possible because this function is going to be called a lot. So because I think in most programming languages a large case switch will be implemented as a jump table, and jump tables are reasonably fast. At least they are faster than 10 times if else, if else, if else. So this is the Pythonic equivalent of a jump table. So we have a dictionary here with functions, and we have here our value. So you want to set an 8-bit register. Here are all our 8-bit registers that you can set. F is not included in here because you will never set that. You cannot set that by hand. And then we have here all those functions we've seen above here. So for instance, you put in, I want to set register B with a certain value. Then this will be called, and I think this is it. So I think I've done this a little bit wrong, so I'm going to change this up a little bit. I think what we need to do is we need to take this val and put it actually just in here. So I'm going to look that up real quick on the documentation. Yeah, here it says if elif 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 is a substitute for the case switch, but I don't want to use that. I want to save every little. I want to save as much time as possible. Yeah, so this is the where I got the idea to do it like this. And yeah, I actually see I need to remove the parameters over here because I will just set it as a function. So it will be a little bit like functional programming. I'll actually use the objects as a value, and then you can execute them here, and I'll specify the parameter. What I also just thought of, but I haven't done yet, is all these functions, they need a self argument. I need to add a self parameter. I haven't added that in yet, but I'll do that off screen because that's really boring. So yeah, so those are the getters and setters. So I need to do this for this stuff too. And put val there, and I need to remove them here as well. Let me see if I got some viewers. Nope. Okay. And these don't take our arguments, so this will be fine. I also built this function, set flag. I'll add this self. So this is real simple. I took this from the documentation of the Game Boy. We have 4 flags. 0, n is something like the previous operation was subtract or a add. Then this will be 1, and there's some other case I think. H is half carry, so that is when the 4th bit will be carried over, and carry is a normal carry, so when the 8th bit will be carried over. And here are our functions that we built previously. So yeah, and here I built a decode function. So not sure how I'm going to do this yet, but it will be something like this. I'll just make like pseudocode for now. So first of all, we need to get the instruction opcode from the program counter. So the program counter will hold a memory location, and the memory location we need to fetch what's in there. So then, after we do that, we need to fetch additional parameters. So some instructions may have 1 or 2 additional bytes of, well, not opcode, but some kind of parameter, so memory location or a value, and we need to get that. But some functions, like a NOP instruction, they don't have an additional they don't have something like that. So then I need to execute the appropriate command, and then we need to like increment program counter, and we need to set flags. And between this is the actual decoding. So decoding will be something like we have, just like I've used these tables over here, we will have values in here, and those values in the dictionary, Python dictionary keys, they will point to a function, and those functions, that will be these kinds of functions. No, not these kinds, these kinds. And then it will pass the parameters into those. Yeah, so it will be a little bit difficult, for instance, because I don't know how I'm going to pass the parameters of those functions into it. So some functions have 1 parameter, some have 2, some have none. I need to figure out how we are going to do that. But to get going, the first thing that I'm going to do is going to look at the only the instructions that are actually in the BIOS. So something that we looked at previously. We'll just hex dump it here. So we have this BIOS, and these instructions, I'm actually going to only implement these instructions just for the time being, and then we'll start with that. So I'm not going to implement every single instruction right away, because that will take a long time. And one other thing that we need to figure out is how we're going to test this system, because the chance of me making an error is reasonably large, considering we have so many functions with all very specific instructions. Some need to increment flags, so a lot of stuff to do. So just a quick quick sneak peek. I will be doing something like this. So I will be doing something like the keys will be integers, and I will do something like this. So for instance, let's say 12, 13. This is an instruction. I don't know what instruction this is, but and I will think I'll use a subdictionary, and that subdictionary will hold the function, that we'll use to so there will be something like this, R1, R2. So that's the myself implemented instruction for this thing. And then we also have something like how many cycles does it take. So let's say this takes 4 cycles. And maybe something like flags affected. And that will be something like so 0, and any other information that we need to include in this. So for instance, how many positions the program counter must be increased. So for instance 6, or 6. So we have like 2 say 4. 2 registers specified, each 1 byte, for instance. Then we need to increase the program counter by 4. And then we'll have this dictionary, and we'll have it for all instructions. So it will be a very large dictionary, but this will hold then all the decoding information. And then maybe I'll do something like this. And we'll hold arguments, let's say 2 arguments. Or even more, another subdictionary with like what argument does the argument is an address, or stuff like that. So that's what's coming up. I'll leave this here for next time, and I'll see you guys later.